Okay, so I think we can start my talk. So it's about the Geant4 simulation. So as Jianlei said, it's a bit technical. So I will introduce following. So first I will let you know some a big structure, big picture of the Geant4, and then I will introduce each component of Geant4. And then we also have some examples, so maybe you can have a look at this example so you can get more familiar with Geant4, and then is a summary. So first, I think one important thing is that you need to know where to find the Geant4 resources. So actually, Geant4 official website provide all this necessary information. And also, it has a so-called event category. So in that category, you can find all the previous tutorials, courses, and also workshops. So you can have a lot. You can find a lot of good tutorials. So, for example, my lecture is based on this previous talk. And also, Geant4 provide a complete document, so you can find all this information here. And also, you can find the source code on this URL. So it's provide all the previous versions of Geant4. So this is very useful if you need to, for example, upgrade your Geant4 version to a new version. Then you can do the comparison. Okay, so let me first introduce about the Monte Carlo techniques. So if you are familiar with Monte Carlo, so maybe you know. So this is the technique to do some random sampling, and by doing this random sampling, and we can finally get some results. So the application is not only in the physics and science, but also in a lot of areas. So for us, the Monte Carlo is very important because it helps us to understand, for example, the detector in the experiment, and study like the systematic errors, something like that. So this is quite important. And in this course, we are using Monte Carlo for the particle tracking. So that means we are simulate a particle and let this particle interact with the material, the matter. So this is what we did here. And this is an example of Monte Carlo. So you can use Monte Carlo technique to estimate pi. So the idea is very simple. So first, you have this 1 times 1 square, and then we can shoot the points randomly in this area, and then we can do a count. So for this, so we need to make sure the radius is less than 1. So that means this green area. So if you have shoot a lot of points, then you will get this estimation of the pi. So it should be the pi over 4, so and equals to this number. So this is an example. So at beginning, so it's not converged. So you can see a lot of a very big fluctuation. But if you have more and more shoots, so you will get a converged results. So you can see this is the Monte Carlo results over the serial pi. So you can see it's almost close to 1. And for the particle tracking, so actually the physics serial for the particle tracking is actually quite clear. But the problem is that if you want to track a particle in a real detector, So it's very difficult to use some analytical formula to describe the whole response. So that's why we use the Monte Carlo technique. So especially when the detector becomes very, very complicated, so the Monte Carlo technique is become more and more important. So then let's see, what is Geant4? So Geant4 is a toolkit developed for the Monte Carlo simulation of the interaction of the particle and with the matters. So the toolkit is developed, I think, more than 30 years ago. So it considers a lot of things. For example, the physics processes, and you can customize your detector and material, and also you can simulate different particles. And also, Geant4 provide a lot of functions, so you can do the tracking inside Geant4. So the Geant4's source code is written in C++. So this makes sure the computing performance could be also important. So and also it takes advantage from the object-oriented software technology. So if you look at the source code, you can see there are a lot of like class and object, and also the code is actually open source. So this is very important. That means you can extend the Geant4 physics if the current physics cannot fit your requirement. So an important thing is that Geant4 is a toolkit. So that means that's not like an application. You just download it and you can run it. So what you need to do with Geant4 is that you are using this as a toolkit. So that means it's like Geant4 itself provides a lot of components. Then what you need to do is that you are put all these components together and to make it work as you like. So I think we can, so go fast. So first, I think one important component in Geant4 you need to know is that called the Run Manager. So this is very important because all the simulation is controlled by this Run Manager. And it manages like such as the event manager, stepping manager internally. So you don't need to care about how for example, the stepping is done. You just need to know we have to create this Run Manager. And also for the Run Manager, you need to initialize the simulation conditions, like you need to set up the geometry, you need to set up the particles you need to simulate, and also the physics you need to simulate. So this is some classes you can find in Geant4. So because as you know, the different users may have the different requirements. So Geant4 provides such an interface. You can to extend all this base class. So for example, this the user detector construction. So this is help user not help. It is used for construct the geometry, and for the physics list, it is used to set up all the particles and all the related physics. And then for the user action, so this is very important. It provides the interface for the users to get all the necessary information. Okay, so for the detector construction, so what you need to do is to derive from the base class and then construct your own detect construction object. So you have to describe the complete geometry setup, including their shapes and their materials. and also their positions. And there is a function called construct interface. So this is a pure virtual method. So this will be used by Geant4 Run Manager. So you have to do all the things inside this construct. Then inside this construct, what you need to do is first you need to construct all the materials, and also you need to describe the detector geometry. So for the geometry, it's you need to precisely describe the geometry as the real detector. Finally, you have to return a pointer to your geometry. So we call it word physical volume. So that means you need to put your detector inside this word and then return this pointer to the Geant4. Okay, so I think maybe we can skip some technical things here. And then the second part is about the physics. So we have you have to create the physics list. This is there is a base class called this user physics list. So you have to put all the necessary information here. So for the list, physics list, there are two major parts. One is to construct the particles, and another is to construct the physical process. All these are actually pure virtual, so you can do a lot of customization inside this code. I think, yeah, we can just skip. Yeah. So here this physical list is quite important. So you have to make sure all the necessary information are set up correctly. So we can go to the next. So then you have to shoot some particles inside your simulation. So this is done by the so-called primary generator action. So inside this, there is a method called generate primaries. So we call this particles primary tracks. So for each event, so it will be invoked, and you will create some particles for this event, and then Geant4 will use this event to do the real simulation. Okay, so I think we can just continue. Yeah. And then there is the user action. So you need to put all the necessary actions inside this action initialization object. So yeah, so there are several levels. Like you can get the information at the run level, at the event level, or even at the track level and the stepping level. So it provides the very important interface to the users to retrieve this Monte Carlo truth information. Okay, so I think we can just go fast. Then let me move to the basics of Geant4. So I will go through this part. So first is about about details, a bit details about how to construct a detector in Geant4. And then I will talk about how Geant4 do the tracking and about some very preliminary information about the physics. And then I will talk about the physics list, and then followed by the user action, and also user interface and visualization. Okay, so first is about the detector construction. So in this part, there are two parts should be mentioned. So one is about the material, and another is about the geometry definition. So all these are very important. So for the material, actually, Geant4 follows the nature one. So we have the so-called elements, and also the elements can made of the isotopes. So there are three main classes to describe this information. For example, this is the bottom level. So you have the isotope. So you can describe the properties of the atoms. You use the Z and N and A to describe these isotopes. And then different isotopes can construct, can made element. So this is called element, G4 element. So you can have the effective atomic number and the effective number of nucleons, and also the molar mass and number of isotopes. And then based on this, we can construct the real materials. And this material can made of the elements, and also the material itself can made of the different materials. So that means you have the mixture in the setup. And an important thing is that you have to make sure all these objects are unique. So this is very important, so you can avoid some problems. Okay. So first, for the material definition, you must have the density defined. This is always done set by the user. You can also set the material temperature and pressure. So this is the default temperature and pressure here. And the material state can be solid, can be liquid or gas. So here is some, this is the, so how to define the solid and the gas is actually depend on the density and threshold. But you can also set this is a solid or it's a gas. And Geant4 also have a predefined materials. So this is called the NIST material database. So this is also very useful because especially when you start your simulation, you may not familiar with how to construct this material. So you can first reuse the materials predefined here. And if you found that the material cannot meet your requirements, then you can define your own materials. Okay, so for the elements, so the construction, I just show some real code here. So the construction is very clear, I think. So first you need to define the name and its symbol. And you can also define you also need to define the this atomic number and the mass. And so this is an example if you have the isotopes. So what you need to do is that, for example, you construct the uranium 235 and the uranium 238. And then you can do a combine. So you need to add these two isotopes to this uranium element. So you can also specify the abundance. So this can be also always done by yourself. So very flexible. And then after you have all these elements, then you can construct the material. So for the simple material, you can just use you can just define the material and use the element you want to use. So this is a very simple example. So you see it defines the uranium and you specify the Z and A and also the density. And you can also define the chemical things. So like you can define the water here. So you have to first construct the hydrogen and the oxygen first, and then you do the combine. So you construct this this water here. So and you can specify how many atoms of each element. So by defining this, you can have a material defined. And also here you can see this is an example of the mixture. So for example, our L contains different components. So this example just show you how to construct this L. So I think for the details you can look at my slides. Yeah. Yeah. So there are more examples. So this is a more complicated one. So you can even combine the different materials and also the elements together. So this is and actually in the real case, this is what we did. So because the material itself, it can be very complicated. So you need to use this way to define all this material in Geant4. And I think another important is that most of you may use this NIST material database. So it already includes more than 3,000 isotopes. So this isotope composition covers a lot of things here. And for this and for the elements, you can also find them. So how to use this? So you can just construct this NIST manager. So this is a singleton object. So you can retrieve it everywhere in the code, and then you can use this method to get, for example, the element here. So so the usage is also very simple. So you just invoke this method to get what you need. Yeah, and also it defines a lot of materials. So there is a command you can list all the available materials defined in Geant4. So you can also try by yourself. Yeah, and Geant4 have some convention for this. So so for this name, so it will have the prefix G4 and then the name. So they also have several definitions, so you can use it. I think for these details, I can just skip maybe. Yeah. So this is an example, another example to get the material definition. So you can see it already defines a lot of materials. Yeah. So this is what I just mentioned. So actually, when you start the Geant4 application, so you can have an interactive environment. So in that interface, you can execute the following the commands. It's like a command. So you can print all this necessary information for you. Yeah, and also you can use the C++ code, source code, to control, so to invoke this method to list the necessary materials. So it will print to the screen. Okay, then let me move to the geometry description. So if you are, if you need to construct a detector from scratch, so then this part is quite important, especially when you do, for example, the detector R&D. You need to change your detector frequently. So you have to be familiar with all this work. So in Geant4, you have to construct a real detector in the computer. It consists of several levels. So first, you know there is some called solid. So this is like defines the shape, and you also have the logical volume. So this is some volume that you can you just construct, but the position is not placed. And you also have to construct the so-called physical volume. So this is the volume that you have already assigned it with some fixed position and also rotation. So this is called physical volume. And the geometry description can be actually very complicated. So a very good suggestion is that you should organize the whole detector in a modular way. So then you can control you can do the replacement very easily. So first is about the solid. So solid is the shape, defines the shape of the geometry. So there is a base class called G4V solid. And on side, based on this solid base class, there is a lot of predefined shapes. In Geant4, we use the so-called CSG. So this is called the constructed solid geometry. So to define all these preliminaries, so like you can define the box, tubes, and some more complicated is like the torus. And also you can have some special CSG, like you can have the polygon design. And you always needed some three-dimension the parameters to define these shapes. Yeah, and this is actually from the Geant4 user document. So in the user document, you can find a lot of other shapes, and it also gives you the instruction. So what's the meaning of each parameters? So here is an example of the box. So in this box, you have 4 parameters. The first is about the name. So you always need to give it a unique name here. And then is the 3 parameter is this is actually the half length along the XYZ axis. So this is if you are familiar, you are new to the Geant4, you just make sure these variables are actually half length. So make sure you are use them in a correct way. And also when you use this value, so you should make sure you also consider the units. So this is also very important. So by default, Geant4 already predefined some units. So you should always use them. So that makes your code more clear. Yeah. And in this example, so the shape is, for example, in the along the x-axis. So it's from the minus 30 to 30, and for the y-axis, so it's from the minus 40 to 40, and for the z-axis, so the value is from minus 60 to 60. So this is how the shape looks like. So when you do the a very complicated construction of the detector. So, but you are actually always start from these very basic units, and then you try to combine them to make the complicated geometry. Yeah, and this is just some example here. And then after you have this shape, so you need to define the so-called logical volume. Because in that shape object, you don't have any material information. So that's why you have to define this logical volume. So in this logical volume, so you can see there are several necessary parameters. The first is about the shape pointer. And then you also need to assign the material here. And then you have to define the names. So this is just a very simple example. So you can use this solid and you use this material to construct the logical volume. And then for the physical volume, because the logical volume is not placed into the like its mass volume, so the physical volume is used to do these things. So this is in Geant4 how to place the the volumes can be implemented in different ways. So that's why in Geant4 it uses a so-called base class, abstract class, so called the G4 physics volume, and then you can see there are different implementation. Like you can have a placement volume, and also in the detector in some detector you can see there is some replication. So that's why Geant4 also provides so-called repeated volume or replica volumes. So that's used to construct a very complicated detector arrays. And also, if you have even more complicated requirements, so Geant4 also provides the so-called parameterized volumes. So you can make you can make the shape even bigger or shorter, smaller, and also you can place it in the different positions. Okay. So what we use in most of the time is the so-called G4 the physics volume placement. So it's a PV placement. So this represents just one position, and you have always need to associate a physical volume with it, and then you also need to define the transformation, and also you need to specify its mass volume. So in Geant4 there are two ways to represent the relationship between the mass volume and the Data volume. So you can just choose one. So this is just a simple constructor. So you can use. So first you can specify the rotation of the volume and also the translation of this volume. And you have to specify the current volume is this one, and then you have to specify its mass volume. So this is very important. And another thing is that for the Data volume, you should not, the shape should inside the mass volume. You should not larger than this mass volume. So that's some requirement from Geant4. Yeah. And also, if sometimes you have to place the volume multiple times. For example, in this morning, you can see the Juno detector. We have a lot of the PMTs. So in the real simulation, we have to place it a lot of many times. But a problem is that you have to identify which PMT it is. So in Geant4, so there is the so-called the copy number. So this is used to help you identify which PMT it is. Okay, so this is a very simple example. So you can place the target into a word volume. So this is simple. Okay, and I think this can be very technical things, so I can just skip, and maybe we can discuss if we have time. Okay, then let me move to the second part of Geant4. Is about the how Geant4 do the simulation, and something about the physics. So I think this will be very useful for you. And in this part, I have several sections. So from the tracking particles and the physics process, and also I will mention what is the so-called production threshold. And also I will cover the several physics modules here. Okay, so first I think in Geant4 you need to understand how it works. So Geant4 have several main components during this tracking. So the first is the so-called the tracks. So as you see in this diagram, so different particles are, so we can call it a track. And you can see, for example, this track 1 have created this track 2 and track 3. And then the track 3 can create its own secondary, like track 4 and track 5. Then for the track 4 and 5, they can create their own. So you need to understand how it works. So especially this relationship between this mother volume and its daughter volume. And you can see in the simulation, so Geant4 actually simulates the step by step. So in each step, it will invoke multiple physics processes. So these physics processes define when and where the interaction will occurs, and also what's the final states, if it will decay or it will do some other things. And also another thing is about particles. So this I think this is simple, so I don't mention here. Okay. So in Geant4, when we do the simulation, so because you see in this example, it will create a lot of secondaries. So how Geant4 handles this tracking is by using a data structure called a stack. So a stack is like, for example, you have a basket, you put something first, and you can put it more and more things into this basket. But when you get things from this basket, you are actually get it from the last one you push. So this is called the last in, first out rule. So then let me explain this structure. So first, when we have the primary generator action run, so this will create the track 1, and this track 1 will be pushed to the stack. So then in this stack, you will only have one track, and then the next in the next step, Geant4 will get one track from this stack. So because there is only T1 in this stack, so T1 will be popped. So you can see P1 is here, and then Geant4 will do the simulation. And during the simulation, you can see it creates two secondaries. So it's T2 and T3. So when it is created, so for example, T2 is created first. So it will be pushed to the stack first. Then T3 is created, so T3 is pushed later. So after you simulate this T1, so in the stack, you will have two particles, the T2 and the T3. And then then Geant4 will do the next simulation. So it will pop the next track from this stack. So because currently T3 is at the top, so we have to get it. So then we do the simulation of the T3. And then you can see T4 is created first, and then it's T5. So then you can see in the after the simulation of T3, so in the stack we have three particles: the T2, T4, and the T5. So then if we do the next simulation, we will get the T5 from the top. So you can see T5 is simulated, and then the T7 is created. So T7 will be pushed into this stack. So then after the simulation of T5, we can get the T7 from this the top of this stack. And for T7, so because it don't produce any secondaries, so there is nothing pushed. So then after the simulation, you will only have two T2 and T4 in the stack, and then you have to pop the T4 from the stack, and you simulate this. You can see we create the T6. So the T6 will be then pushed to this stack. So after all these processes, so Geant4 will find, okay, so there is an empty stack. So that means the event is stopped here. So then you can see if you look at the order of how Geant4 pops these particles from the stack, you can see the final simulation order is like this. So it will simulate T1 first, then it's T3, and then T5, and then is T7, and then you will go back to the T4 and T6, and finally is T2. So this is the whole structure, and also you can use a very useful command to print all these processes. So it's called the tracking variables. So it will be very useful, especially when you are new to Geant4. So you can see all the steps and all the positions and all the interactions it happens, what it occurs. Then let me move to the about the particle definition. So in Geant4, so this structure is like this. So first we have the some static, so it's called intrinsic properties like the mass, the width, its spin, and lifetime. And then for addition to this, we also have the related physics. So it is managed by the so-called process manager. So that means for each particle, you can have one process manager. And then for one process manager, you can have multiple processes defined here. So Geant4 follows the rules from the particle data group, so-called PDG. So it also follows the Monte Carlo numbering scheme here. For example, you use 22 to represent gamma. And in addition to these PDG particles, Geant4 also defines its own particles. For example, it defines the so-called optical photons. So this is actually different from the gammas. So you can think there are two different particles in Geant4. And also in Geant4, there are some special particles called the Geantino. So you have the without charge or charged Geantino. So this is very useful to track your geometry is set up correctly or not, because there is no additional interaction with the material. So you can see is that track follows your serial. And for the charged serial, charged Geantino, it can know the field. So, for example, if you are in the magnetic field, so you can have the do this, travel like this. And in Geant4, the short-lived particles, especially the lifetime less than this one, are not transported by Geant4. But Geant4 have some decay tables inside, so it can do the decay. And also Geant4 have some light ions, so you can see here like alphas. And for the more heavier ions, it is represented by a single class called G4 ions. So, but inside it has different mass and different Z and A in the construction. So you can still identify what the ion it is. Okay, so this is a list of some tables. So you can find most of useful particles here. So for example, for the electron, so it's called the G4 electron. And during the simulation, if you get the PDG ID, so it's 11. And for the positron, so because it's opposite of the electron, so it has a negative 11. And for the muon, so we have muon plus and minus. So for the muon minus is 13, and for the muon plus, the PDG is negative 13. And also it has a tau and also neutrino here. And also we have the gamma, so by default it's 22. And for the optical photon, so in Geant4, so actually there is no defined PDG. But sometimes for your convenience, you may override this PG number, so then you can get this number directly. And also you can see there is a Geantino here. Okay, then let me move to about the physics. So here the physics actually help you answer how do a particle is interact with the material. So there are two responsibility of the physics process. So first, it is used to decide when and where an interaction occurs. So for example, in Geant4, there is a so-called physical interaction length. So this is to limit the step size. And also, you see, if we want to do the calculation, so we need the cross section. So this is defines the probability. And also, Geant4 have a special process called the transportation process. So this is used to make sure the particles are travel always inside the same volume instead of it go outside. So the transportation process will give you the boundary limitation. And the second responsibility of physics process is about generate the final state of the interaction. So this is also important. So for example, it will, when you do decay or you create some secondaries, the original track, the momentum will be changed. So this is all done by this so-called final state model. So so if you look at dive into the Geant4, you can see there are a lot of models can be chosen. So yeah, this is also very important when you want to do some validation between the Monte Carlo data and the real data. Maybe sometimes you need to do some tuning of the model. So in Geant4, it have a base class called the G4V process. So actually, all of the predefined physics processes are derived from this base class. And it defines some very common interface. So you can see here, so Geant4 divides these actions into three categories. So first is called at rest. That means a particle is already, it don't have any energy, kinetic energy, so it just stops here. So what happens with this particle? So this is so-called at rest. So you can see the process like the decay and the position annihilation will be related to this action. And another is, let me show here. So it's called a long step. So that means when a particle moves from this step to this step. So during this step, it will create some continuous particles, like we can for example, the example of the ionization. So it can create a lot of electrons here. So this is all done by this long step. And then we also have the post step. So this is more like some point-like interaction. So for example, the decay in the flight and also the hadronic interaction. So all these are done by described by this post step. And actually, a process can be implemented by combining all these actions. So this is an example. So we have for example, the pure. So we only have one action. So for example, the discrete process, and we have the Compton scattering, the hadronic inelastic, and for the continuous process, we have the Cherenkov effect. And for the at rest process, we have the muon capture at rest. And we also have the combine the rest and the discrete. we can have this position analyzation. And for the continuous and discrete, we have this ionization. So this, for example, we can create the delta electron from the simulation. So this delta electron is actually created by this discrete action. Okay, so then let me talk about, because we have multiple processes related to one particle. So how these processes work? So actually, this is called stepping. So stepping is help you invoke all these predefined, all these processes. For example, for the along step action, so it will try to cooperate. So it will invoke all these along step action. But for the post step or the at rest action, because only one physical process will be happen, so then there is a compete. So the Geant4 need to know in this step which process will be invoked. Also, there is some additional information like it calls the forced or conditional force. So this is some like an extra requirement on the physics process that makes sure. For example, if we want to always make sure the transportation is done by Geant4, so we have to make this as a forced. Yeah. And then let me discuss about the invocation sequence. So the first case is when the particle is still traveling. So at the beginning of this step, so first we need to determine the step length. So what Geant4 did is that it will invoke all these related processes, and these processes will give Geant4 the length of its the propagation of this length. So that means for different processes, it will give different lengths. Then Geant4 will do the balance. So it will choose the smallest length. So that means if one process gives the smallest length, then that means this this process will be invoked. And also, then we can invoke the along step action because you already know the step, so you can invoke all the necessary physics processes related to this along step. So this will do the you will combine some results. For example, the deposit energy, something like that, at this stage. So after that, so it will apply the post step. So this will done also in sequence. Yeah. So another case is when it is at rest. So when this particle is at rest, so if it's already stable and cannot do invoke any other process, so then we will Geant4 will kill this particle. So so-called kill. So then the state of this particle will be marked as killed. So for this for others that will be do more actions. So we will determine the lifetime first. So it's actually similar to the length, but we are using the time in this case. And for example, if this particle have several different at rest actions, so we will choose the smallest one, and we will think this one is the final action. It is invoked. So that's how Geant4 do the stepping. And then when we do the simulation, one thing is that because the simulation can be time consuming, so in a traditional Monte Carlo solution is that if this particle, the energy is lower than some threshold, we will just kill this particle. So this is, I think it's a very simple idea, but the problem is that it can cause some imprecise like stopping location and deposit energy. So then Geant4 use a different way. So Geant4 don't have the so-called tracking cut. That means Geant4 will always simulate a particle when it is the energy is down to 0 or it's decayed. So that makes the simulation can be more precise. So how to control the simulation time is that Geant4 using the so-called production cuts. So let's call it W0. So this is like a cut. So decide if the secondaries the secondary energy is larger than this threshold, then this secondary particle will be created by Geant4. Otherwise, if this energy is lower than this threshold, so Geant4 will not simulate, will not create this particle. So we will just use the deposit energy instead. So that means there is no secondary created. And also there is some applies case. So you can see here. So like for the gamma, the ionization and some hadronic inelastic scattering. So yeah, so that's especially when it creates some secondary electrons. So this production cut is very important. When we discuss this production cut, so actually Geant4 use the called range instead of the energy, because the problem is that if we are using the energy, so in different materials, their response will be very different. So that's why Geant4 choose this distance instead of the energy. So by default, if the secondary cannot travel 1 millimeter, so this is default value. So this secondary will not be created. So the energy will be just deposited into the energy. Also, so Geant4 will do some internal conversion actually. So it will convert this range to some energy threshold, but that will be different for different materials. Yeah. So we always need to do the balance between the accuracy and the computing performance, because if we have very small production cut, so maybe it is very accuracy, but it will take a huge CPU time. So that's is not affordable. So we need to do the balance. Yeah, so this is show you some example. So this is 500 megavolts electron volts proton. So travel through this sampling calorimeter. So you can see this is like a sandwich. So we have the liquid argon and this. So this, liquid argon should be the sensitive, and for this is not sensitive, the passive. So if we have the cut in energy, so you can see that for this passive region, you can also create a lot of secondaries. So it will also take a lot of time to do the simulation. But if you set this cut too high, so this thread too high, so in the sensitive region, you can see there is nothing created. That's not what we want. So what we did is that in Geant4, you just define a range. For example, you have the range in 1.5 millimeter. So if the secondaries can travel longer than 1.5 millimeter, so this secondary will be created in the liquid argon. Otherwise, the secondary is lower than threshold. So for example, in this passive region, so nothing will be created. So this can save a lot of computing resources. Yeah. So, but in the real case is that in some simulation that a different region can have different precise have different precision. So then in Geant4, it introduced another name called the region. So that means you can define a part of or a collection of detector volume as the same region, and then you can assign the different production cut into this region. So, for example, here there are several examples. We can have different production cut for different material or different detectors. So this can be useful to speed up the whole simulation. Especially we have the very complicated detector construction. And Geant4 also provide another thing called a step limiter. So in some cases, you don't want to this particle go too far. So for example, in some like the silicon detector, you want to have a very precise position, precision. So we have to use this like so-called step limiter. So it will do some. So when the step is longer than this limitation, so Geant4 will give it like a force cut. It will stop it at this position. So this is can be done if you register some additional physics module. So by default, Geant4 don't have this limiter. But if you need, so you need to register this physics module. And you also have to define this limitation for this volume. So this is also necessary. Then let me maybe talk a bit about the physics model. Because Geant4 actually it's like a framework. It provides a very flexible way to describe different processes. But actually, sometimes even for the same process, we can have different models. Because for different energy region, you can have different precision. So you can adopt different models. So Geant4 provides this general model framework, and it decouples for example, the cross section and the final state. So then by decouple this, people can, the developer can just focus on a special region. For example, focus on if the final state is not correct, so it can do more correction in the final state generation part. So Geant4 actually provide a lot of models and also the cross-section. Yeah. So for the electromagnetic physics, so there are because this is actually very normal. So we have to use it every time. So Geant4 provide a complete list of all these models. So by using this, you can see there are different the energy region can be a bit different. For the very low energy, so for example, this Livermore and this Penelope model can be used. And for some maybe higher, so you can have different models here. So I think this can be actually you can do the balance. So if you want to simulate very, very precise do the very precise simulation, and the energy is actually low, so you can adopt this low energy model. Otherwise, you can choose some so standard model. Yeah. So in Geant4, there are several packages for these EM models. So you can see the standard for the muon, for the X-ray, and also the optical, and it also covers the so-called high energy and the low energy, and for also the polarization. So for the gamma rays and electrons and positrons, so for the so we have the several things like the gamma conversion, the Compton scattering, and also the photoelectric effect, and also maybe sometimes we need this scattering, yeah. And for the positron and electron, we have so all this like ionization and this mass scattering. This model, this process are actually shared for positron and electron. But for the electron, so it also has the annihilation. So you can see you have to register additional process here. Oh, and then for the so muon, so we have the muon ionization, and also these processes. I think due to time limitation, I just show you. And if you want to look at the details, so Geant4 has a physics reference manual, so you can look at the details about this. So for this EM standard model, so this standard is just the standard, not the particle physics standard model. So yeah, so this defines some traditional, I think, the normal configuration. So this can be used in most of the cases, and you can already find a lot of process here. And for the CPU consuming, it also is not so intensive, CPU intensive. So it can help you save a lot of CPU time. And we also have the low energy models. So they call the Livermore models. So Geant4 group have extract some data from the some published Livermore database. So it then extracts them and then to do the combination again, and then create this Livermore model in Geant4. So this is this model can be used, for example, in the medical and some underground or real event search experiment, and also in the space experiment. So there is also another called Penelope. So this is based on some simulation codes called the Penelope, and it also provides the low energy description. So you can use it for the low energy simulation. Yeah. And so as I just mentioned, because in most of the cases you can just use the standard the EM model. But if you have to use some, you have to study the low energy case. So you may need to enable these low energy models. And so if you are using simulate some physics higher than MEV, so just consider use standard. So that will save a lot of CPU for you. Yeah, I think maybe this I can end here. Yeah. Okay.
Thank you, Tao, for this very nice talk. Questions? I have a first question about the beginning. You said you showed the example how to estimate pi using random numbers.
Yes.
But as we know, the computer don't have random numbers; they have single number.
Yeah.
Random. How will this affect that we don't use real random numbers, but epsilon and random numbers bias the results of simulation? Do you know some?
I mean the real random number.
Huh?
You mean the real?
No. We use always pseudo number
pseudo.
generators. So do someone research how this bias the result of simulation? So I know that there is hardware random generators that actually gives you real random numbers, but it's very slow and number of bits per second. If compared to pseudonumber generators, but as pseudonumber generators are not random in nature, so does someone research how this may bias the result of simulation? How will it different if you use a real random generator from the hardware and the pseudonumber generator? These two simulations. Don't you know some
maybe I'm not. I don't know the if any research focus on this, but in Geant4, I think so. So in Geant4, actually, it uses some random engine. So internally, it have like more than 100 state number to. So that's cause that makes the reputation even very impossible. That it makes sure the unique of each number.
No, it's not question about unique. The question about this is not real random number. So don't someone search the difference. What will cause this that we use pseudo-random generators and real random number generators? No one searched this difference.
I'm not sure, but
I think there might be some difference, but I'm not sure how to prove this.
Yeah. So currently, I think most of us are using the schedule random. Yeah.
So the repetition length is so large.
It's not a repetition. This is the nature of random numbers. So you use. It's a bit different question. So it's not about the period. It's about the nature of the random number generator. It's not really random. It may cause some difference bias in the results. The question is there is some research in this question? In this maybe there is difference, or there is no difference. It is not insignificant, this difference, because it's we rely all our research or data processing on the random number generators. Okay, so we should know they reliable. And the second question is about the matter. So actually, you when you say about materials, you mean the pure materials in sense there is no impurity. For example, some dust. Not, for example, isotopes. So which will use some noise. For example, if we're talking about optic photons propagation in the matter. For example, in water, in liquid scintillator, some impurity will give you deformation of course, wavefront, and could we simulate in these impurities? Oh, it will be waste of time, because in statistics we will always have this will neglected difference.
So currently, I think, for example, because I did a Juno simulation, so we didn't consider such like a dust in the material. But I think the dust can impact on the absorption length. So this absorption length is actually measured from the real data. So I think this effect is actually impact on this length. So, and this length is used in the simulation.
So as I can understand you correctly, you use ideal simulation model and compare it with the physical results, and the difference is, of course, it's some unideal of a real system. So it's noise, dust, and etc. So you take into account, and then you process the compare simulations and compare with the real data. I understood it correctly?
So I'm not sure if I understand correctly. So what we did is that, for example, you mentioned some isotopes. Yeah, this can be actually modeled in simulation. But if you mention some the real dust, I think we don't have. But if we really have the dust, so this will have the impact on the real measurement, right? So this actually is the input of our simulation.
Geant4 gives
Yeah.
this interface, putting some effective dynamic capture that effect, rather than you simulate to wait for
some waves
the photon to scatter on the impurity molecule.
Yeah.
For example, when I listen lecture about Juno, if I don't not mistaken about the name, they talk about the radiation, natural radiation.
Yeah.
So of course cannot 100% make a pure material.
Yeah.
Of course.
Yeah.
So do we could simulate this that we have about maybe 0.1% of impurity in the material, or this will be waste of time? And
no, I think it's over time. Yeah. So actually, what we did is that we can do the estimation. So, for example, how many dust inside this material, and then we can estimate the rate of the background. Then in the simulation, we can just generate this like the gamma or alpha directly in the simulation, and then we see what's the final detector response it looks like. Yeah, but we actually don't simulate the dust itself.
Yes, that's great. In other words, you don't simulate the real thing, you make ideal thing, and the difference you use in the input parameters.
Yeah.
Okay, thank you.
One question.
Thank you for your lecture. I have a single question. If I need to simulate an isotope with atomic number greater than 110, maybe what should I do?
Yeah.
Sorry.
You mean atomic?
Atomic number greater than 110. Super heavy element.
Some what?
Super heavy.
Super heavy.
Super heavy.
I think currently maybe cannot model
No,
maybe.
anything in the database, no problem.
Yeah.
It's not in the database.
So you mean some extra?
What's
Some-
the heaviest? I lost track. It's 110? 110 is the heaviest? Yeah, if there's nothing existing in the database, you
Then
can
I-
make something up. But
Yeah, maybe you can extend this, but I think by default Gen4 don't.
by default, it doesn't.
yeah.
So normally you have to write a generator.
Yeah, because also you need to consider like the physics, right? So you need to extend everything maybe. Yeah. Because Geant4 focus on the normal, like electron, positron, something like gamma goes through this material. So it just models these things. Yeah.
Thank you.
Thank you for your presentation. I have a few questions. As I understand, in Geant4 we work with point-like particles with defined momentum and coordinate, yes?
Mm-hmm.
So nowadays it's relevant sometimes to work with wave packets. So are there any tools to modulate these situations in Geant4, or maybe in future you plan to include it?
I think currently maybe not.
Okay, you
Wavelet,
don't know?
yeah, no.
Okay, thank you.
Yeah, I wonder though, I mean, people doing, it must have some capability of doing that. So I think that people who does radio, I mean, the radio wave interacting with ice, for example, they also use Geant4. But I mean, typically it's designed for particle like this.
Yeah.
You know, it's,
Because it's relevant.
when you're using, radio detection of high energy neutrino, they use Geant4. But I mean, there must be something.
But they are actually focused on the the rest part, right? Interactive with the detector, not the.
Wave part.
No, but if the radio wave is generated in the ice, don't they use Geant4 to simulate how it?
Yeah, but I think
Radio
the
wave.
is the detection part. When the radio
Yeah.
makes them simulate.
I think they maybe have some
That's right.
different models to do this calculation.
Right. So they can track certainly radio wave impact. They can certainly track.
But I think that maybe looks like a generator. So it generates the particle arrive at the detector level.
Yeah.
Maybe not the propagation.
So
yeah.
waves, Geant4 is not simulating, but this can be done separately. And then the effect of wave can be simulated.
Yeah.
Okay. Other questions? You have one.
Yes. Thank you. I also have a question. Do we have simple access to various cross sections and other things, like in terms of functions or classes? Like if I would like to draw, for example, d over dx or some, I don't know, some.
Yeah. So actually, Geant4 has some classes. So like some if you say ddx some calculator, so you can actually invoke this calculator to get the under database information. That's possible.
Mm-hmm. Do you plan to show something like that?
Oh, I don't have the full plan to show this.
Okay.
Yeah, but it has this interface.
Okay.
Yeah.
Thank you.
So one trick I learned from my student is that before you look at all these PBS files, tutorials, and now if you have a question to Geant4, you just use ChatGPT. It tells you all the code.
Okay, ChatGPT.
So the learning curve is so much shallower than I did it 20-some years ago. So seriously, they write all the code, they teach everything. So ask them to tell you how to get that database file. I'm sure it's a one-line code. ChatGPT will just like
Thank you for your lecture. Maybe I have some questions for the Geant4. For one problem, maybe from the high energy simulation for the muon. As we all know, the chemistry net has detected one muon with the energy above 100 keV. So as mentioned in your lecture, the muons can be simulated in Geant4 is around 1 keV. So I'm not sure how to simulate this high energy muon in this Geant4.
I think some, like for example, some people they have extended the existing physics list to support this ultra high energy region. So I think I'm not sure, but maybe you can find that physics list if it's open source. Yeah.
Thank you.
Yeah.
And there is another problem. I'm not sure. I'm considering that if in Geant4 can we simulate like the detailed simulation like from like the dark noise generated from PMT. Like I'm not sure.
Okay, so dark noise is actually not simulated by Geant4, but normally we have an additional step after detector simulation. It's called electronic simulation. So we will add the dark noise at that level.
Oh, okay.
Yeah, not at the Geant4 level.
Thank you very much.
So if I still have some time, I would like to remind people, sorry. So because, make sure, because we have some examples, right? So make sure you already look at the documents, I think. So, yeah, tomorrow, yeah. But just a reminder, because people should download the, sorry. Yeah. Yeah, so in this, the third part, so you can see there is some instruction. So actually, we have prepared some so-called Docker image. So the Docker image is like a virtual machine, but it's quite lightweight. So please have a look at this website. So it will give you some instruction. And if the network is not very good, so you can download I think that there is an existing table already provided. So you can download them and then import them. So I just show you the, yeah. So so if you access this GitHub web page, so we already have some instructions. So so if you have a very good network, you can just or you already downloaded, then you just use it. And if you are not download them yet, so please download this table file. So and then you import it into your own machine, and you should make sure you can run some tests. So this is some instructions. So if you want to do the visualization, so make sure you have enabled this X server. So you need to allow the Docker process can access this X server. And then when you start the container, so it's like a virtual machine. So make sure you have specified this environment variable, and also you do the mount of your local X11 directly to the Docker image. So after that, you can start the GUI. Otherwise, you cannot do the visualization. Okay, that's just a small minor comment. Yeah, thanks.